We're looking at Unit 2 today. We're starting trigonometry, and 2.1 is talking about angles in standard position. That's found on pages 74 to 87 in your text. Our curriculum outcome is 20.4, where we need to expand and demonstrate understanding of the primary trigonometric ratios, including the use of reference angles, where your angles between 0 and 360 degrees, and the determination of exact values for trigonometric ratios. Our lesson objectives: number 1, we need to learn when an angle is in standard position and what that looks like. Number 2, we need to learn what a reference angle is. Number 3, we need to be able to use special right triangles to find exact values for some angle measurements. And number 4, we need to apply the concept of special right triangles to some real life situations. So an angle is said to be in standard position when its vertex is at the origin on a coordinate plane and its initial arm is along the x-axis. So here's our coordinate plane. Here's your vertex, and that's where the two arms meet, and this is called your initial arm, so it has to be along the x-axis. And this other arm is called your terminal arm, or where the angle ends. So this would be your angle here. Each quadrant of the coordinate plane can be numbered, and a range of values for an angle whose terminal arm ends up in that quadrant can also be labeled. So this is quadrant 1, and those are angles from 1 degree, or I guess 0 degrees, all the way to 90. In quadrant number 2, you're looking at angles from 90 to 180, not including 90 or 180, of course, because those are the angles that would be a right angle and a straight line. Quadrant number 3 is from 180 to 270, and quadrant number 4 is 270 to 360. So a reference angle, this is a key term for us today, is the measurement of any angle measured to the nearest x-axis. And this concept is extremely important to understand for future lessons and other courses entirely. So here's our coordinate plane again. So if I said that this angle that I'm drawing right now had a 35 degree angle, then I could draw another angle over here in the second quadrant where this is 35 degrees. And that would be 180 minus 35, which would be a 145 degree angle. Likewise, in quadrant number 3, you could draw another one that's 35 degrees away from that x-axis. So that would be 180 degrees plus 35 degrees. And that would be 225, sorry. 215, sorry. And then you could draw a fourth one where it's 35 degrees from this side. And that would be 360 degrees minus 35, which would be 325 degrees. So we're going to take a look at something called special right triangles now. And in trigonometry, it's extremely important to memorize the side lengths of two special right triangles. One of those triangles is a 45, 45, 90 degree triangle. Another one is a 30, 60, 90 degree triangle. So here's our first one, 45, 45, 90. Now, if these two angles are both 45, that makes this an isosceles triangle. And that means that these two side lengths are also the same. So I'm going to give this a side length of 1, which means this also has a side length of 1. Now, if I want to find out what this side is, well, I will just use this Pythagorean theorem. So 1 squared plus 1 squared equals x squared. And that means 2 equals x squared. So x equals root 2. So that means in every 45, 45, 90 triangle, the ratio of these sides is always the same. This has a side length of 1. This one has a side length of 1. This side's always going to be root 2 times bigger. So if this side length is 5, this is 5 root 2. If this side length is 100, this is 100 root 2. Now in a 30, 60, 90 triangle, things are a little different because we can't make an isosceles triangle. But what we will do when we label the triangle is we'll give this a side length of 1. Now our next step is to just create exactly same an equal triangle on the other side, like a reflection, which means that this is 30 degrees and this is 60 degrees. So now you can see, I guess this would have side length of 1 as well. Now you can see that these three angles are all 60 degrees, which makes it an equilateral triangle. So all the side lengths are also equal. So if this whole side length is 1 plus 1, which is 2, that means that this side length is 2. So now we've got the short side having a ratio of 1. Second, the longest side is twice as big, and we need to find this other side. To do that, we'll use the Pythagorean theorem again. Now we have 1 squared plus x squared, because we don't know this long side. And that equals your hypotenuse squared. So that's x squared equals 4 minus 1. That makes x squared equal to 3, and so x is equal to root 3. So in a 30, 60, 90 triangle, your short side is always 1, your hypotenuse is always 2, and your long side's always root 3, which means if this side here happens to be 5 meters long, this side will be twice as big, 10 meters long, and this side will be root 3 times bigger than 1, so that would be 5 root 3. So now we're going to find some exact values of trigonometric ratios. So we can find exact values, which means no decimals or rounding, of sine, cosine, and tangent of some specific angles by using these special right triangles. So the first one is 45 degrees. Well, remember that 45-degree angle triangle has sides of 1, 1, and root 2. So say we're looking for this angle right here. That's a 45-degree angle. And so sine of 45, if you remember your sine ratio, that's always opposite over hypotenuse. So that's 1 over root 2. Now remember that we seldom write this as with roots in the bottom, so we'd multiply the top and bottom by root 2, and that gives us root 2 over 2. And that's an exact value for sine 45. If you wanted, you could take and put this in your calculator, root 2 divided by 2, and you could also then see that that's going to be the same thing as if you put sine 45 in your calculator. So cosine 45 is then the adjacent side over the hypotenuse. That's 1 over root 2 again, which gives you root 2 over 2. And tan of 45 is opposite side over adjacent, which is 1 divided by 1, which gives you an answer of 1. So these are the ratios that you should know. You're going to use them a lot in the next couple of years. That sine of 45 is root 2 over 2, cos 45 root 2 over 2, and tan of 45 is equal to 1. Now for 30 degrees, we need to use a different triangle. We're going to use a 30, 60, 90 triangle. And remember that we had a 1 here, we had a 2 here, and we had a root 3 here. If this was 60, which makes this side 30, or this angle, sorry, 30. So sine of 30 is opposite over hypotenuse. So opposite, which is 1, over the hypotenuse, which is 2. That's just a half. Cos of 30 is adjacent over hypotenuse, so that's root 3 over 2. And tan of 30 is opposite, or sorry, yeah, opposite over adjacent. So 1 over root 3. Now if we multiply by the top and bottom by root 3, we get root 3 over 3 as a final answer. And finally 60 degrees, we can still use this triangle. That sine of 60 degrees is opposite over hypotenuse, so that's root 3 over 2. There's your opposite side, there's your hypotenuse. Cos of 60 degrees is adjacent over hypotenuse, that's a half. And tan of 60 degrees is opposite over adjacent, so that's root 3 over 1. We just leave that as root 3. So there's your exact values of sine, cos, and tan for 45, 30, and 60 degrees. So here's an example. It says the arm on a grandfather clock moves between 45 degrees and 135 degrees. What horizontal distance does it move through if the arm of the clock is 150 centimeters long? So let's just draw this. We'll use a little coordinate plane. It says that it moves from 45 degrees all the way through to 135 degrees. Now, and they're looking for the horizontal distance. Well, if I think about it, this 135 degree angle is just a reference angle of 45 degrees, or the reference angle of 135 degrees is 45 degrees. So I really just have these two triangles that are 45 degree triangles. So that means I'm looking for the horizontal distance here, which is x. So what I've got here is a 45, 45, 90 triangle, and I know that the length of the arm is 150 centimeters long. So in a 45, 45, 90 triangle, I know that these two sides have a ratio of 1 to 1, and this side is root 2 times bigger. So now that I have the hypotenuse, it means that these two sides are root 2 times smaller. So that's 150 divided by root 2 centimeters. Now, if that's this distance, 150 divided by root 2 centimeters, and then this one over here is also going to be the same length. So I really just have 2 times 150 root 2 centimeters, which is 300 over root 2 centimeters long. Now, if we're going to write this appropriately, if they want the answer in exact form, we're good here, but we do need to have roots out at the bottom, so I'm going to multiply the top and bottom by root 2, which gives me 300 root 2 over 2 centimeters, which is 150 root 2 centimeters long. So in summary, We know an angle is in standard position if its vertex happens to be at the origin and its initial arm has to be along the x-axis. The terminal arm can be in any of the 4 quadrants. We know that a reference angle is a measurement of any angle to the nearest x-axis. So say we're talking about an angle measurement of 160 degrees. Well, 160 degrees would be in quadrant number 2, but the reference angle would be 180 minus 160, which would just be a 20-degree reference angle. So you're always measuring to the nearest x-axis. We know that by using special right triangles, we can find exact measurement of sine, cosine, and tangent of 35, 45, and 60 degrees. Not 35, 30 degrees, 45, and 60 degrees. And we know that these triangles then our ratios are 1, 1, and root 2 for a 45, 45, 90 triangle. And for a 60, 30, 90 triangle, then we know that it's a 1 down here. We know that the hypotenuse is twice as big. We know the longest side is root 3 times bigger than the shortest side. So your assignments on pages 85 to 87, 83 to 87, sorry. Good luck, and we'll see you in class.